Start.
Hello everyone, thanks very much for coming. We're very pleased today to welcome Professor Lindsay Hutley, who's a professor of environmental science at Real. So Lindsay is widely known for all his work on carbon and water fluxes in savanna environments. He's also worked more recently on mangrove environments as well. And so he's published prolifically on these topics and other topics. I've actually counted just before coming. You might not know, but you've published 184 papers so far. So it's pretty impressive.
There's a few probably erratums in there as well.
still. Yeah. And there's another impressive stat about Lindsay, is that he's been a CDU employee for 25 years. So he's just hit the mark last week, I think.
It's a long sentence, that one.
Yeah. I can't imagine how many restructures you've been going through and survived.
5.
Yeah.
Well, our
and name changes.
Name changes about 2.8 years. Yeah. 2.8 years. It's a coefficient in a model. Yeah, we're on track.
Pretty impressive. And yeah, so Lindsay today will be sharing with us his latest research. So it's TERN-enabled research, TERN being the Terrestrial Ecosystem for Terrestrial Ecosystem Research Network. So basically a network of flux towers, among other things. And so there's 5 flux towers across the NT, so from the coastal, high rainfall coastal areas down to the arid zone. And so that's what you will be mostly talking about. Yeah. Awesome. 90%. Please join me in welcoming Lindsay.
Thank you. Thank you very much for coming along. I got a bit inspired by Donna's talk on TERN a few weeks ago. I thought, oh my God, I've been here 20,000 years. I've never ever given a talk on TERN. I don't think we could look up the records, which probably don't exist because the Institute's names turn over every 2.5 years. So they're probably all gone. So I thought, oh, I better get off my ass and tell a tale with all my colleagues. Well, TERN is a network, which means there's lots of colleagues, which means there's lots of people that don't necessarily have their name on here, but we'll focus on the NT bit of the TERN ecosystems processes facility is what we'll focus on today. So that's the startup photo is you can see, and they're very important. Probably the most important person in this network is this guy. He manages the infrastructure on behalf of TERN. That's Matt Northwood. And you can see him sort of gazing happily up at this little bit of kit that's sitting on a tower. Have a look at that big smile. And that's obviously the sensor network all working. It's online, it's happy, it's calibrated, and Matt's is a happy man. There are other times when Matt's is less happy, but we'll get to that. So anyway, let's, without further ado, turn it up, monitoring mass and energy. I use the word mass. I could have put carbon and water, but I thought it's actually a bit broader than just carbon. Everyone's obsessed by carbon, so it's water as well. Let's see if all this works. Not so far. No, I do. Here we go. What are we going to talk on? What is TERN? Who's heard of TERN, out of curiosity? Apart from a few obvious. See a lot. Well, Matt, you don't count. Stefan doesn't count. Who has not heard of TERN? Okay, yes. So most people have. Not a great sample. You should have. It's good to know that you have. So TERN, Terrestrial Ecosystem Research Network, is what it actually is. So we're going to talk about what it is, how it's structured. We're going to talk about some of the measurements we'll be making, a little bit of background on the technique, scaling and modeling. The importance of scaling and modeling TERN is well the bit we're in, Master and I are in, and Stefan Meyer up the back there is a site-based network, and so making measurements in a single site is relatively useless unless we've got some method of spatial extrapolation in space and time. Might look at a few applications of what the data has and have not been used for, and maybe I think, yes, where we're headed and what some future options. So that you're a very literate audience. We don't need to labour this point too much, but of course the climate's changing. That's CO2 concentration. I was a bit surprised we're at 420 parts per million. When I started measuring CO2 in the 80s, we were sort of roaming around with our ergers saying it was 340 parts per million, so it's quite a lot. That's a rapid rise, 2%, so showing no signs of slowing down. And of course, that's driving temperature increases. This is the temperature anomaly, maximum temperature of the NT. We're probably about +2 since 19th turn of the century. much less gradient in rainfall, but we are also wetting very slowly. About 120 millimetre mean annual rainfall has probably increased in the last 100 years. That's the NT. Most of you will know that probably the Kimberley is wetting a little faster. But we're wetting, we've got more CO2, and we're getting a higher temperature thermal regime, driving probably higher incidence of extreme climatic events. We're all aware of that. And I guess that's now reflected in quite a lot of literature. This is a new textbook just published last year on global ecosystem collapse. Who's in trouble? Where are these systems? And what are the drivers of that stress? And there's a chapter in there that I was sort of involved with on the mangrove dieback in North Australia. That's been highlighted as an example of ecosystem change, or at least an event where a system has gone backwards. Dana Bergstrom has led a paper recently, 2021, again, same sort of theme, combating ecosystem collapse from the tropics to Antarctica. A pretty Australian focused paper, that one, but it's worth looking at. This is another nature climate change, same thing, biological responses to press and pulse. That's missing, it should say press and pulse. Climate trends and extreme events. What are these extreme events doing to our ecosystems? This too is this is entirely Australian focused, so Harris et al. So there's plenty of this sort of literature around. And of course, no surprises really, given this sort of event. We are now seeing some sort of impact in North Australia. This is the mangrove dieback. You can't quite see. It's going to be tricky here, Robin. How do we get rid of that? Is there an ability to hide that?
Just get your mouse on it.
Get your mouse on it? Off it. No, never mind. That is a photograph from a helicopter at about 100 meters in the Limon area of Northern Territory. If you can see the whole photo, there's about 20 kilometres of pretty much 100% dead mangrove stems. This is an Enso driven event, driven pretty much by a very rapid tidal drop. Prior to that, there was 3 or 4 poor years, below average rainfall years, and a moderate heat wave. But what killed them, we think, is this Enso-derived tidal drop. So the range of tidal ingress is possibly, there's areas along this coast that probably not had any tidal mixing for up to 6 months. We've got the LiDAR data from this landscape. We can match the tidal record to the LiDAR data. We had a master's student calculate the timing of tidal dynamics on this landscape, given we had a really accurate DEM from a LiDAR flight that we commissioned in 2017. And sure enough, a lot of these forests actually had no tidal mixing. In other words, they were sitting there for up to 6 months in high temperatures, very low moisture levels. We had a sediment that's hypersaline, probably on the way to being oxygenated with very little moisture in there. You'll see cracking, you'll see oxygen penetrating the soil, the sediment. It's quite sandy sediment in this coastline. It's not a mud, it's probably a muddy sand. And the co-occurrence of these variables has led to this catastrophic event. And that's also fairly well documented down in the literature. Never mind, we'll cut.
And the next thing down.
Down to more.
The high control. No, next one. That one.
There we go. Oh, perfect.
I wasn't just checking Facebook link.
Oh yeah, how wonderful. That's the real support network kicking in there from the head of department. So I guess it's a happening thing in our environment already. There's been some evidence of savanna tree dieback in the VRD reported in the last couple of years, probably following the 18 and 19 low or monsoon, near monsoon failure, and that was reported a lot of cattle stations dialed in. NTG's been promoting that as an event. That we've seen savanna dieback, which is pretty unusual, pretty rare. That's happening, and then the so-called mulga dieback in Central Australia that's also been reported. So these events are really happening now. So we have to be aware of what's going on. Solutions. Well, I had another look at the Bergstrom paper, and she's proposed what she calls the 3 A's pathway. I don't know how novel this is. It's a sort of a management framework that the authors have proposed: awareness, anticipation, and action. 3-step management framework. What is awareness and anticipation? Adaptive management steps prior to an ecosystem collapse. So awareness, understanding what are the biological ecosystem services being provided. Anticipation, I'm assuming some sort of modeling framework, some sort of predictive capability, and then action. What the hell are we going to do about this? And mitigation, avoidance, and try and reduce impacts. And there's their sort of adaptive cycle. I would commend you to have a quick look at that: awareness, anticipation, and action. So I thought that's quite interesting. Does that flavor or help us interpret, that's the wrong word, but understand what the TERN Ecosystem Research Network could actually be doing? Because based on what we are doing, I suspect the services that TERN is designed to deliver are pretty much along the lines of that management framework, the 3 A's. So it's an ecosystem observatory is the sort of thematic structure, and there is our inverted cone. And last month, I think you heard Dr. Donald Lewis give a very nice presentation on the middle bit, which is regional scale monitoring sites, this ecosystem surveillance program. The bit I'm going to talk to today is this bit here, right at the bottom: ecosystem processes. Pretty much a sort of a smaller scale, local scale monitoring, and particularly the focus is on carbon and water cycling. And so this is the why and the how, the what and the how much. We have a regional to national site network where we're monitoring vegetation change. And of course, the whole thing at a higher level is continental scale monitoring. TERN landscapes is the third facility, and really that's the remote sensing community. That's sort of fancy speak, politicians speak for remote sensing capability, site monitoring network, and ecosystem processes, functional ecology at a site scale. So site, region, continent, and of course, interactions and engaging with all 3 of those facilities is fundamental to the network. And the outcomes that pop out, I guess, the data to support research and modeling is really primarily focused on supporting infrastructure and getting quality information about how our ecosystems, what are they, where are they, how are they functioning, and what state are they in through time is the idea. To do that one. And that's us today. Okay. Bit of text. So site-based provision of data to quantify responses and resilience of Australian ecosystems to climate change, disturbance and land management. So this is long-term monitoring of ecosystem state. And here is where we're really interested in the structure of vegetation, change in that vegetation, carbon and water budgets, how they change through time. And of course, what is the biodiversity on that site? Is that changing well? So you're trying to link structure, who's there, what's there, with carbon and water cycles, all in the one hit. So that's the one goal: contribute model ready data for simulation of ecosystem processes. So this is when we bring in the modeling and the remote sensing community, extremely important linkages to expand, extrapolate from that, some point-based, site-based measurements we're making across the country. Engage with land managers, industry, agriculture to better quantify carbon sequestration, the biosphere and the pedosphere, the soil. And that's a newer sort of goal, certainly the last 10 years, where I think TERN has done not a great job linking with industry, it's fair to say. And now, of course, the carbon cycle is of prime interest now to land managers around the world. How can we link? How can we use these data in a fairly pragmatic way? Engage the public. I'm not totally convinced TERN's on anything on engaging the public, but it's certainly a good goal. And that's about recognizing and valuing the natural capital of our natural ecosystems and our agricultural ecosystems. They really do to be in good shape. And then finally, I'll put this in low font. Really, ultimately, I mean, that's not a direct goal of TERN, but it probably should be an indirect goal. Ultimately, what's the point if you're not going to try and influence policy? Change the way we function. So that's perhaps our awareness. If we link it again back to the Bergstrom framework model, management model, this gives us an awareness of ecosystem processes, what they deliver, what they don't deliver. Anticipation, in my mind, that's how we link to the modeling community. We can predict heat stress, we can predict drought stress. What will it do to production? What will it do to biodiversity? And without the sort of fundamental knowledge that we, in theory, are collecting through the TERN EP network, that we won't be able to answer those problems. So this is how we can help facilitate ecosystem modeling to the next level. And action, is that really the action? Perhaps that's contributing to the actions required in a small way, as is 0.5 or goal 5. So there's the network, TERN EP network across Australia. You'll see the words supersites and Ausflux sites, kind of confusing. That's the network as it stands at the moment. It's a bunch of sites around Australia through the various bioregions of Australia. And you can see quite a cluster of sites in the north. That's us. What is a supersite? That's us. Supersites is where we've got this carbon and water monitoring happening, but we've got a site that's effectively near pristine and is considered to be a really great site to represent one of those biomes. And a good example, I guess, is the savanna supersite up here. There's 16 of them around the country that are representing those long-term. So these sites are getting a bit more, if not quite a bit more resources than those Ausflux sites. There's more of those Ausflux sites. The Ausflux sites pretty much consist of a flux tower and some basic ancillary measurements. What is the vegetation there? What is the soil? Whereas the supersites is a much more intensive operation underway, where there's an attempt to monitor canopy cover change, how the vegetation changes through seasonal time and through interannual changes. There's a lot more emphasis on linking the flux measurements to remote sensing, and a lot more emphasis on biodiversity assay. So the Savannah Supersite was Litchfield, tabletop range at Litchfield was selected, and a key player in all of that in the early days, 10 years ago, was Stefan Meyer, who selected the site because of its value as a remote sensing site. A lot of the other Ausflux sites are quite a bit smaller, may or may not be suitable for remote sensing. So the beauty of the Supersite program, the site only makes it onto the hit list if it has some key attributes that make it even more powerful to invest in. The other beauty of the Supersite, like Stefan selected, was that it had some old NT government veg monitoring and fauna monitoring. They've been going back to the 90s. So ticked a few boxes, and I'll show a picture of it in a moment. So that's the concept of the Supersite. The functional metrics we're interested in, linked to biodiversity, canopy structure, ongoing. Not sure why I put that back up again. There may have been a reason. Of course, the flux technology we use, the measurements of water and carbon exchange and energy is, of course, duplicated around the world. So we are part of the Ausflux Supersite network in Australia. We're also part of this global Fluxnet measurement. And the beauty of this, of course, it's an international network where the same methodology, has been rolled out across all the biomes of the world. And that gives us, in near real time, a great way of monitoring what the ecosystems of the world are doing. And it probably follows the density of sites, probably links to GDP, I reckon, given the size of North America, Canada, Western Europe has got an incredible density, 90% of it you can't see, whereas the African systems, which are of enormous importance to global CO2 dynamics, global energy exchange, has 4 to 5 sites, of which it's conceivable 2 or 3 are not functional at the moment, depending on funding. Some of our little blobs are in trouble at the moment as well, but there is fantastic data to be had from this network. You can see there's some huge gaps. For example, there's nothing in the Amazonia. There used to be in Marland, right about there, but that's not even on the map at the moment. And we all know the Amazonian basin, again, has global importance in terms of controlling or influencing global patterns of weather. So the Amazonian system has just become a net source to the atmosphere. It's traditionally lasted, as long as it's been monitored, it has been a sink. It's no longer a sink. Too many heat waves, clearing, issues like that have now flipped the cycle, we're losing more carbon than we're gaining. I noticed this, I was surprised that there was no site there. So a great network. We're part of it. All our data that we collect through TERN is all open access. All of it also gets sent to Fluxnet internationally. And so a lot of modeling communities or modelers, remote sensors, pick these sites up around the world and use it. I think we've got one of our sites, well, I'll get to that later. So what are we doing at a site? We've got interest in leaf to ecosystem scale processes is what we're interested in. Photosynthesis, water use, energy balance. At leaf scale. And also to a stand scale, a canopy scale. So this is a drone shot of the Savannah Supersite. Partners, very important partners. Flat, beautiful, flat environment. Is it representative of the Savannahs? I guess, maybe not. That's why we have a network, but a terrific site. And here, of course, we can monitor all the key ingredients of understanding how mass and energy is exchanged from our landscapes. So we're measuring rainfall, we measure incoming and reflected solar radiation. We can also measure the net heat exchange from the landscape back to the atmosphere. Evaporation rate, which is effectively evapotranspiration. In other words, we've got a pretty good handle on water use, vegetation water use. And the other thing we're measuring is CO2 fluxes, the net flux. The amount that's coming in via our photosynthetic pathways, and of course the amount that's disappearing back to the atmosphere. And the method is quite powerful in that it's seeing water from anything, our water use, our heat exchange is derived from all elements of the landscape, be it soil, grass, material, trees, bark, whatever. The whole lot is being captured. So all our CO2 is reflectance of the current cover at that particular time, as well as picking up other processes that are incredibly important, such as respiration, soil respiration, respiration from the elements of the ecosystem, grasses, trees, etc. The weakness, I guess, though, is that we only get knowledge or a number that encapsulates the entire system, including the soil. So you have to be aware of that. Fantastic. It really is an ecosystem scale measurement that you've got here. But to actually separate out the tree, the grass, the various elements, the deciduous, non-deciduous, evergreen elements of the flora, a much more complicated story. The other, well, there's some trace gases, and there, of course, is the cost of doing this. So the instrumentation, because you are measuring with as much precision as possible, some really reasonably difficult things to measure, plus you need someone to look after these systems, not quite 24/7, but regular. So there's a lot of effort goes into keeping the system alive. So that effort to set this site up we started that journey in about 2012, I'd reckon that. It's now 2020, whatever we are now too. So a 10-year journey to get the site, negotiate with the partners, Indigenous sign off. They need to know what's happening on their country. Construction design, designing all of the infrastructure, designing these arms that enable rapid management and monitoring and maintenance of the equipment, all essential. How do we measure radiation accurately? Do we measure it there? Do we measure it there? Where are we going to put our instrument network? Given the site, given the questions we're asking, we're interested here in fire and climatic variability. What's that doing in our landscape? It's a very fire-prone area. Anyone who follows the North Australian Fire Information System, that part of Litchi does get a lot of fire. So that's part of our thinking about how we interpret the information. So fantastic information, a great site for remote sensing. Of course, thanks to Stefan's efforts, he is doing highly detailed measurements of canopy dynamics through time. Because all of these biogenic changes, heat, evaporation, net CO2 are really very much coupled with the amount of soil, the amount of moisture in the system, how much leaf area we have in that landscape. And as you all know, our savannas have a hugely dynamic leaf area, fractional cover, wet to dry. So measurements in the wet are not necessarily anything or well, they have a relationship, but they're very different from measurements in the dry season. So we have to have that really accurate seasonal pattern before we can start to work out annual sums of how much carbon is coming in and out of this system and back to the atmosphere. That's a bit on the methodology. The methods we use is called eddy covariance. It's simple, it's a brilliant system. We won't go into the detail, but basically, as we have lateral airflow through a surface, a crop, a forest, a wheat crop, could be anything, a rice paddy, whatever, you'll generate turbulence, you'll generate an eddy spectrum, and that eddy spectrum, the energy in that is also transporting CO2, water vapor in and out of the canopy airspace. So as CO2 rich air comes from the lower atmosphere, that's immediately absorbed by vegetation, and you'll find that the concentration of CO2 as it leaves the system is depleted. We can measure that. We can measure the rate of that depletion. In the night time, you'll have the reverse process where there's there's no more photosynthesis, so the respiratory fluxes are dominating. And again, the eddies will be richer in the internal relative to the above canopy box. Whole bunch of mathematics. We need to have assumptions of relatively uniform, flat terrain, which you saw from the drone photo of the Supersite. That's box well ticked. And from that, we can calculate every 30 minutes, we can estimate how much net mass and energy we exchange between the land surface and the atmosphere. Very powerful if you're doing accounting, very powerful if you're a climate modeler and you need to know what is the energy exchange of the land surface with the lower atmosphere. So we tick a lot of boxes there, not only some knowledge of carbon accounting, but hydrologists in the room are interested in the fact that we not only measure carbon, we measure water, and the climate modelers are definitely interested in the heat balance, the albedo, the reflectance of this environment, how that changes through time, because we've got net radiation measurements, we've got the long wave and the short wave balance. We've got sort of most of the components covered. Best mass, we haven't bothered about that, but that's our key metric there. What I did say is if we have a sensor that's can measure this scalar. This scalar could be carbon dioxide, water vapor, could be temperature. And from those three values, we can calculate the net sequestration, either be it dominated by photosynthesis or respiration, how much water we're losing, how much energy we're losing via a sensible heat flux. And of course, if you bolt on a methane sensor, or even an N2A, if you've got a lot of money, you can measure the methane emission as well. So it's quite a versatile setup. But the key ingredient is rapid. All these sensors are rapid response sensors. They spin very quickly to capture those eddies, because those eddies are doing the work. Okay, so we won't labor this point too much. From that, we can calculate a sink. The daytime measures give us photosynthesis, less the respiration. At night, there's no photosynthesis, of course, no sun. Any measurements we make at night, once we've dealt with a few assumptions, gives us the net respiratory loss from the ecosystem. This bit often gets left out, especially in carbon accounting. And don't forget, respiration has got quite a strong thermal response, where photosynthesis does not have quite the same thermal response. So of course, if we've got a warming climate, a warming atmosphere, this term in our carbon balance could really get quite large. And so we really need a good handle on respiration. So all our nighttime values are representative of respiration rate. And from that, we can then also derive the gross primary production. What comes in? Some amount will disappear back in the atmosphere. We've got plant respiration, soil respiration. The leftover bit is that bit, NEE or NEP. And then, of course, we need to know what disturbance is. So that might be fire in our landscape. And all of these metrics are relative to the atmosphere. This is also, I guess, a powerful tool that we now know what's coming in and out of the atmosphere, because we are concerned about the impact of that variable on our biological systems. And once we do a bit of mathematics, we can work out what the disturbance losses are. We can come up with this longer term net biome production. And this guy, he's involved. This is after his boy band career just ended. This is Clem. He does some fantastic work of working out what's coming out of the system in terms of drainage, the movement of carbon, dissolved organic carbon, dissolved inorganic carbon, through soils, into groundwater, into streams. Is it stored in wetland systems? And then how much of that's released back to the atmosphere? And if we're not accounting for that bit, are we overestimating these bits? And perhaps we are. So it's very rare that we have someone like Clem that works alongside the group of, that are working on this terrestrial carbon balance. So here we're trying to get a bit further along the track where we're trying to link terrestrial processes to the aquatic system. And that's what Clem's expertise is in. And he's got a DECRA and a discovery to do just that. So that's a great example of a linkage we can make in this world. So we might speed up a little. So these are our factors we get out of our flux measures. These are really biological processes. This is photosynthetic rates. This is a respiratory or biochemical processes. And this is our water use. All of that's controlled by stomatal conductance, water stress, soil evaporation rates. And as a result, all of these factors that we're measuring on our site, we measure all of this, helps us understand how these change through time. Rainfall, soil moisture content, soil air temperature through the canopy. This is VPD, vapor pressure, evaporative stress index. How dry is the atmosphere? All the growers will tell you, as soon as that air dries out, crops can struggle. This is a really important atmospheric metric that does feed back onto these fluxes via stomatal regulation, limiting stomatal conductance, limiting stomatal aperture. How much cover we got on the site and what's the background CO2? Because we know photosynthesis is driven by CO2 concentration. Once we've computed all those, we can get a bit funky, we can sort of start working out water use efficiency. So how much carbon have we captured per unit water loss? Again, growers are particularly interested in that. It's a fairly commonly used indice and metric. You can use it for natural systems as well. So if this starts to move around rapidly, we know there's potentially some stressors in the system. Radiation use efficiency, a similar concept. And even if you've got a nitrogen balance, how much carbon do we sink per unit available nitrogen? So in an endoportrait system, such as a natural savanna system, that also has got environmental, ecological meaning. So these are what we call our ecosystem functional attributes. Again, we can derive all of this information because we're at this supersite where we have not only the fluxes being measured, but all these other properties of the ecosystem. Then we go another step further and we can bolt in well in the supersite again. All of these metrics are being measured as well. Microbial, we do eDNA surveys where we can see what's in the soil. Rather primitive at the moment, but that's the goal, sampling that through time. We know about the soil, what's the soil type, what's the soil nutrient contents, what's the soil properties, soil structures, all of that we know at every site. We do a little bit of monitoring our plant animals as well. And of course, very important for us, how does disturbance modify these processes as well? And a big one for us is fire. We've also done a bit of work on cyclones and storms and pest outbreaks. So you put the whole lot together at a supersite. That's the goal of doing this. That's why we do it. So it's not only the physiology, but it's the ecosystem attributes and these attributes, these site attributes that are really important to capture long term. So you can build up a more comprehensive knowledge. So if you had that bit only, that's fine. If you can have all three of these components, that is the concept we're looking at here. All right. So this is me 20 years ago. We'll do a little look at the Howard Springs site. It's been embarrassing, I know, this photo, but that's Tony O'Grady, one of the old timers there. So we started this program in the 90s where we used this elecovariance technique to measure the total evapotranspiration of the whole landscape, because the NTG was concerned or interested about how seasonal is the water use of the veg and how much groundwater or is the vegetation using. A lot, none, what's the deal? And one way or one bit of that equation is to try and get some really good measures of water use by the vegetation. We do the whole swag of stuff on that. But we managed to keep the site going, and now it's been going for about 20 years. So once you get it going that many years, we went out there and we found the old bit of tin in 2017. What appalling site management maths. It wasn't you, by the way. So the litter bugs had left their old bit of tin out there, and that's about the same spot. So that means, though, from that 20-year period, we've got some information about how these three processes are changing. And here's the plot time. This is 01 to 18. We wrote this paper in about 17 and we got to 15 and we messed around for 2 years and screw that. We've got another 3 years of data. Why don't we start writing the paper again? So we added another 3 years of paper. So my slackness actually was about a bet. We now got an 18-year record in this paper. So, but we have got another couple of years. In fact, the years we don't have is 19 and 20. By the way, these are water years. This is a financial year. It's the June to July story where you encapsulate the monsoon in one year. It's just a bit neater. So what do we get? What do we got here? So we've got this gross primary production variable. The red is the ecosystem respiration, all derived from these flux measures. So what we've done is taken our 30-minute averages, summed them all up for the year, and we've got one number that represents each year, or a water year, for gross primary production, the ecosystem respiration. And the bit in the middle is what's left over, and that is the sink. That's what's left in the ecosystem. And the question is, it's quite high at Howard Springs. Where is this carbon going? If it's a sink, it's got to go somewhere. Is it in the soil? Is it down the rivers? Is it fire? Now that data does not account for fire, losses of fire, because the method, a couple of the assumptions in the method are confounded if there's an actual fire running through the site. So we calculated fire losses in a separate process, and these data have that fire period removed. But it still gives us an awful lot of information about the nature of the productivity of the site. And sure enough, it's actually going up. So we've got a statistically significant trend in all of the properties, which we thought was a little higher than we thought. We also looked at the water balance. Its too is going up. Latent energy is the evaporation. This is the evaporation rate. It too is increasing. And this red line is the water use efficiency, one of those ecosystem attributes I was mentioning before. And it too is increasing. So we're getting a more water use efficient system as a result. So what's going on here? We then said, all right, let's look at these trends. So you can calculate the trend and we could work out the trend in the amount of carbon per gram per day per meter squared. And we found there was actually no trend in the wet season at all. There's no significant trend if you just slice up the data and just look at the dries as we go through time, or the wets. And most of the trend was in the dry season. In other words, the period when the grasses are not active. This is a tree-derived change in the land, in the production. So is that a classic sort of water use efficiency CO2 interaction? So what we then did is a model attribution study where we took a model, said, okay, model, here is all of the data, here's the fluxes, here's all the climate drivers. What does the model think is happening at the site? In other words, we asked the model, could it simulate the observed trends? We first asked it, could it simulate anything vaguely like the seasonal dynamic you get? Here we have some of the observations. Ensemble observations. So these are effectively 18, each point is a mean of 18 for that particular day of the year. So it enables us, and this is model data and observation. So let's start here. This is the carbon. The model is also able to split the tree and the grass component as well as simulate the ecosystem, the black line. And there's the observations from our flux tower. And it does a pretty good job. So those two lines in a perfect world would match up. We see the model overshoot here. So this is coming out of the wet season. That's the wet season. That's the beginning of the dry, wet, coming out of the wet into the early dry. There's a bit of model error there. Water, not doing too bad. Here's what it thinks the grass or the understory evaporation is. It's probably about right. It's around 2 millimeters in the wet. We've measured that, not too bad. So the model's okay. It's not perfect. We've got an overshoot there. That's probably because it can't deal with annual grasses. They turn off and the model's still seeing a lot of moisture in the soil, so it simulates a higher GPP than actually exists. But it actually did pretty well when you add all that up. The model and the observed GPP were about the same, not too bad. So we can probably persist. What we did here was a sort of a fairly standard model attribution experiment where we had a climatology, we enabled all the variables, see how we went pretty well. And then we did an experiment where we gave the model just the mean condition and we allowed only one variable at a time or two variables or three variables to vary naturally, and we could see how much of the trend could we predict. And it turns out, won't bore you with the detail, but the most useful coupling of variables where we kept everything detrended, all other variables except for rainfall, air temperature, and CO2. And once we enabled the model to do that, it almost completely accounted for the the modeled trend. So that sort of suggested to us we perhaps have a very classic CO2 fertilization response simply by using the model. We know the model's flawed. We don't really care about that. The trend it's simulating is much higher than the observed trend, but we know it's getting it about right. And we saw quite a strong CO2 signal. So we're asking the model, it is 31 parts per million of CO2 since we started the observations in 2018. Is that enough to expect to see a trend in that production? And the answer is yes, it is. And so we could say, okay, we've now learned something about the site. And at this site, we do see an increase in production, and it's probably due to a fertilization effect. And if that's the case, we've got a classic CO2 response where in the literature you'll see an increase in water use efficiency as GPP goes up. Remember, our production did that, and our water use only did that. Much less of an effect, but the net result was quite a strong water use efficiency. But remember, it was all in the dry season. So if that's the case, you'd expect to see perhaps some woody thickening. And if you look at the satellite, you can see that, but that's sort of what we got. We got a weak trend in the fractional cover for the area around the tower. So you use the remote sensing to see, well, is our knowledge making any sense in the real world? These are actual observations. And the answer is yes, we can probably conclude that this site is responding to CO2. It's a classic CO2 fertilization, climate change effect. So that's one site. That's the story from one of these sites. That's another 30 stories. How long have you got? That's one site. I suppose it's an interesting site. It's a long-term site. A lot of these sites not that long. So don't worry, we're not going to go through that. But we do have other sites along the gradient, and a lot of these southern sites have a very different scenario to the Howard Springs site. Much less fire, much lower rainfall. Some of them are on cattle stations. You're in a bit more of a real-world scenario here. Perhaps far more informative at trying to work out, well, what the hell is the whole rangelands doing in this climate change scenario with grazing, fire, climate change, big swings in rainfall, perhaps some heat waves coming, et cetera, et cetera. So what do we see? We won't spend much time on this, but there's a number of 5 other sites along the NAT, the North Australian Tropical Transect, which was established by CSIRO. And we thought, wow, what a great way of using a natural gradient in rainfall, hold the soil constant, do the same measurements along the gradient. Exactly the same setup, more or less. Now, these other sites are Ausflux sites. They do not have the investment that the Supersite has, and the Supersite's only been going in terms of the fluxes since 15. You can also already see, oh, did I miss Howard Springs? Maybe I did. That's a shame because it's quite informative. No, that's Howard Springs. So that's the sort of 20-year cycle. And you see a spread, there is a bit of a spread in the annual years. So what the hell do these squiggly lines mean? That is the cumulative flux, carbon, GPP in this case, each year. So we start at 0 and we end at some number. That's the number of 30-minute periods in a year. And so each of these points represents a year. And that spread represents, what is the spread of the sort of net primary production over that for each year for that 20 years. So it gives you an idea of the interannual variability. This is what we're more interested in now. So we're trying to work out what's the spatial and temporal variability of this metric, GPP. One site, Howard Springs, does not tell you what this landscape is doing. No way in hell. Here's another site. Now we're down the track. Much lower rainfall, Valley River. It's on a cattle station. And you can immediately see a big spread. That year was a source. These other years have been a sink. So I should also tell you that any number below 0 is a net source, a sink, sorry. Bit of key information you didn't get there. Sink, source. But I'm interested in the spread. So we haven't done much, I haven't had time to analyze these numbers in much detail, but there's quite a rich database here. Here's another site, drier. This is Dry River, west of Catherine. Cattle station again, but well managed, very little weed, not much fire, but again, a huge variability in the fluxes. And if we had the water channel turned on these plots or the net ecosystem, it'll be very similar. So by making these observations in not only time but space, you can build up a much more comprehensive understanding of how the system is bouncing around, how it's going to be moved around by climate change, because you can calibrate a model based on all the fluxes. And in fact, we're measuring all the site variables. Well, this is the Mitchell, this is on Sturt Plains. This is near Elliott on the Newcastle Water Station that we've got people making measurements of groundwater dynamics, et cetera, even also really large. And if I had the data for the Alice Springs Tower, I suspect that interannual variability, if we put on the same scale, would be bigger. As we move into the semi-arid, arid, those interannual variation increases. But we are able to quantify that in terms of these fluxes. What is the system losing in terms of water? What is it sequestering? And again, a number of sites were sources. So that's all quite powerful information. Other applications for the method, of course, putting it at a site. This is another experiment. So those transact measurements are ongoing. Matt runs all of that as well. He not only looks after the Supersite, keeps all these plots down that gradient operational as well. It's an enormous job. And we have one of the highest data continuity metrics, because your instruments fail. I can guarantee you that. Something needs it, something goes wrong. But given his efforts, we have around the country, we have one of the best quality records in terms of the gappiness of our records, pretty low. So experiments, this method is quite powerful because you can use it in a practical sense. That's a fairly sort of theoretical framework. We've got an environmental framework, we've got a modeling community, desperate for this sort of data. That's all quite good. But here we've got a site where we work with the NTG to actually use the methodology. There's the tower again, to quantify emissions, CO2 in particular and methane, from a clearing event where we track the emission prior to clearing, the actual event itself, and then the consequence of soil disturbance, getting the site almost to a crop ready scenario. So I won't go into the detail there, but it's just an example of what you can do with the methodology. We've got something here. This is the Fluvial story, Howard River. We're now at a catchment scale. Here is the flux information here. So this is this concept of understanding carbon processes from a sort of terrestrial environment. But hang on, what the hell's happening in the wetland? What the hell's going into the river? And so the focus of this work, that's another Clem paper, fantastic paper, is really this drainage network. This is actually not superfluous, but a secondary consideration. So Clem says, okay, you guys have got all this information, quite handy. How can I use that in conjunction with trying to work out what carbon movement do we see in this landscape? So again, you can bring these two, this technology together. And that's a whole story there that Clem, you should give a paper on that at one time. That's the next real seminar. But it's just an example of how we can use these methods and approaches in a more thorough way to really nut out where the carbon and the water and the energy is going as we change climate. Here's another example. This is the same technology. There it is again, tower. We're now in Kalimantan, Indonesia. This used to be 40 meter peat rainforest full of orangutans, 30 years of burning and clearing. That's what it looks like now. And here we are, we put the tower equipment in collaboration with ACR, some NGOs in Indonesia. The idea is exactly the same. Here we're in a wetland though, and this site is equipped with a methane sensor. We've got a fast sensor that's measuring methane, because the methane emission from these constantly wet landscapes are extremely high. So we're not only interested in the water, the evaporation, the CO2, but methane becomes very much a component of the greenhouse gas story. So again, it's quite handy technology to work on. And of course, this has got a much bigger sort of component to just these fluxes. This project is much about livelihoods. How can local people use this? It's run by a local community, an NGO run it with some difficulty, but they're doing a fantastic job. Here's a bit of advertising. So we've just published this paper last week where we're pretty much describing, well, what have we learned in the last 20 years from this Ausflux/Supersite network? And so we thought we'd cobble together all the sort of senior people who've worked on it and put out a paper to describe it. Again, we won't go through that. That's available if anyone's interested. And that's got a conversation article that just got published today. We're sort of quite a provocative title, but how are Australia's systems tracking? How can this sort of effort help understand these processes or not? That's out now as well. So what's the future? Clearly, we've got high end in the savanna, we've got very high interannual variability. We can see that from those drier systems, and particularly the last 5 years. But, you know, what's the resilience in the system? Does it bounce back? So I looked at the Howard Springs data for the 2019 year, and or even 18, where we had a terrible wet season. Actually, I saw very little wobble. So perhaps in these high rainfall sites, it will cope with a 40%, 30, 40, 50% drop in rainfall, as long as it's not prolonged. The fluxes were no different. I was quite surprised. So is there some resilience? Does that resilience drop as we drop the rainfall? And perhaps that's where the NTWA Drought Hub that's now based in CDU, can it fund some additional work that focuses just on that ecosystem resilience, sensitivity to temperature, drought, in the NT, on perhaps monsoonal extensive rangeland systems? That's the sort of thing we can do with this information. Think outside the box. And of course, our big client are still the modelling community, and I was interested in this paper. Got published. This is from the ARC Key Centre for Climate Extremes at the University of New South Wales. And sorry, that's not formatting too well, but this student, Lisa Peckin-Tromp, she took probably the world's top 15, or maybe not 15, a dozen of the world's top dynamic global veg models. These are the models that try and describe or predict these fluxes, the storage in the ecosystem, what's happening through time. And these are the ones that then drive the land atmosphere component of global climate change models. So they kind of get the land bit wrong, you get the climate wrong. It doesn't look real good for the sort of Northern Hemisphere designed models. How are they tracking when we try and run them for Australia? And you can see there's a wide range of outcomes. So each line is a time trace. Here we're looking at this production again. And you can see a lot of the models are actually producing a net source where all the observation, and this family of models always producing in this case, the whole thing has been reversed. That's a sink, that's a source, just to confuse you all. But the model spread was kind of alarming. So it sort of says to me, this is the CSIRO model, which is probably the most believable model. But these are all very famous models. These are all the models that all the modelers all the climate guys will go to. And have a look at the carbon storage. It's a pretty big range. So there's some serious improvement in this modelling activity that's required. So your ability to predict climate change impacts from this sort of suite of models might be a little uncertain. And this is the ensemble, which does suggest it's fairly neutral. I mean, all models are wrong, by the way. That's not why you run a model necessarily. But a very great practice is to look at, well, what is the ensemble of all the models? What are they all doing? I was quite struck by the range of model output. And it's perhaps not surprising. One of the biggest uncertainties in the global carbon balance, the entire carbon balance, where we're integrating transport sector, energy production, land use change. It turns out the land sector is one of the biggest, has the greatest uncertainty in the modelling, and perhaps because it's so complicated, where we're trying to predict the net uptake and loss from all biomes across the planet. That is a difficult thing to do. And so this land sector has the greatest uncertainty and therefore needs perhaps the greatest, a fair bit of effort. This is the same paper. We're getting ready to have a beer. This is the same group. And I was interested, they jumped on our data because I think it's pretty good. So that's that's the NAT, where they've taken all these models, they've all run them for the same site. And I guess it's a flag that we're actually doing something pretty good. We're about to be defunded potentially. This work may or may stop, depends on the Commonwealth whether they want to keep us going. We're trying to make a case that we're doing something that's useful. So this, we're now doing a bit of flag waving in the literature, as you can see, suggesting, well, it's got some flaws. The TERN network has definitely got some flaws. It reminds me of myself. It's trying to do too much with not enough skill. So it's underfunded. But, we've kicked some boxes, ticked some boxes and kicked some goals, I think I was trying to say. But have a go at downloading some data from the TERN portal. So that is an enjoyable experience. Good luck. It's a work in progress, it really is, but I think there's some scope. I might end on this one. This is where we plotted the TERN network. There's all the sites. This is the Enso record since 1970. And you can see most of the sites, I've only really seen 2 or 3 of these Enso cycles. So really, we still have a very short, very scattered start-stop. There's only several long-term sites. So that's the Howard Springs site there. That's the Cyro site that's now no longer being managed by Cyro. They've washed their hands of it. It's also been cooked by the fire. So there's some real challenges to keep this all rolling. We're in a bit of a point. So the government might say, no, we just don't think this is worth the investment. We don't get a lot of cash, but so we're at a bit of a crossroads at the moment. So I'm very confident we will get funded, and we're asking for more money, but you never know. So I might leave it there. That's a little website again where TERN data is not being used, but this is what TERN wants to get to, where you've got a bit of a report card. And so you've got temperatures, tree cover, vegetation cover, climate, and soil moisture dynamics, rainfall, blah, 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 analysed for every year. And all of that goes into some sort of index of land condition or environmental quality. And this is a joint project with ANU. They've ingested a swag of climate data, remote sensing data. What they want to do is now perhaps get a climate carbon tracker. So all this data that we're measuring somehow integrated and give each region, so this is the NT of New South Wales, we do it for any state in Australia, do you get another couple of boxes down here, which might be primary production, respiration, or sink strength, or something like that. So that's the sort of thing TERN's interested in doing. They have to sort of be shown to be doing something useful with this taxpayers' money. Is that what people want? Would they find that useful? Hot days are quite a useful thing. Again, I looked up some of the metrics. They're not using the NAFI data for the burn area, for example. They're using generic products, but they can be bashed in the head to get that right. So, yeah. Anyway, that's where we might be going in the next TERN 2.0 if we get funded and we keep our networks ticking. But it's a bit like owning a yacht, these flux towers. It's every constant maintenance. There's always something is not quite right. So it's constantly requiring input. So I might leave it there, Clem. Happy to take some questions. Sorry for droning on.
Any questions?
I can see a few people up the background nodding off. Dr. Ray.
Yeah, look, thanks, Lindsay. That's really impressive. Look, I've just got a question. You commented on the end about how you can use all this information to inform environmental quality, and can you say a little bit more about that? What do you do to link this to environmental quality, and what exactly is meant by it? Quality for what?
I suppose the one you'd probably get focused on is drought stress. Where you could see all of these points in space would end up data into a model, and you have a model that's predicting your water use, carbon uptake, as well as, and as say we have a sort of 2018-19 scenario where we're drifting into a soil moisture deficit, that would be reflected in the sort of carbon uptake or loss. So you'd be showing that your production, I mean, it might be more useful to, say, a producer. And the more interesting thing is to, say, calibrate the BOM's new seasonal forecaster. So they're trying to get a 6-month seasonal forecast algorithm going that's perhaps useful for someone who might be planning land use or as a grower. In other words, if the long-term forecast is that we're going to have a really quite severe La Nina or El Nino cycle, or we've got a drought coming, would you really want to, you know, destock your cattle station or something like that? And then we can, in theory, use some of these data to predict the impact on ecosystem production, even grass production.
Yes, I was thinking more in terms of, I can understand from an industrial production, or, you know, as a cattle example. I'm thinking more in terms of natural ecosystems. What does it mean? You know, look, I'm sure you don't know. I don't think any of us knows. What would all this mean? You know, these changes in fluxes. What does it mean for you know, plants and biodiversity conservation, and what does it mean? I wonder.
What you'd see is that if the production starts to drop, the productivity drops. Is that going to feed back long-term to biodiversity? I don't think anyone could really tell you. I often sit there and look at a gamba grass site, for example. So it's got very low biodiversity, but its productivity actually probably is more because it's punching out 10 tons of grass a hectare for a wet season, for a growing season, and that's probably the equivalent to the natural system. But what you'd see is, you'd see that the interannual variability of that production would be starting to do that. And so you'd have massive fires where the whole thing collapses. You're going to have a massive soil erosion event. It's a shame Natalie's not here. But so you could even use coefficient of variation. So how's this system bouncing around? And as you disturb the system, it's getting extreme environment events, heat waves, mangroves dying, your IAV will go through the roof. So perhaps that's the most useful. What's the interannual variability? How's the system bouncing around? And in the Bergstrom paper, they actually have quite some nice conceptual models where you can characterize a slow decline or a step change or a sort of a wave change. And that's what we could see in these. I think linking it to some sort of predictive future climate modeling might be quite useful. Yeah. But I still think the main utility is getting these climate models much more lined up. Yeah. Coping with land use change and extremes of temperature, for example, in drought. I think everyone's saturated. Speaking of drought.
Lindsay, I'm online. It's Karen.
Hi, Karen.
Could you say a little bit more about the report card idea? Because I think that is brilliant and that would stimulate so much interest in everything that's gone on in the last 20 years.
Yeah, it's a nice way, Karen. I guess it's not unlike the report card concept for Darwin Harbour.
Yeah.
But it'd be a way of forcing the scientists and the users to massage the data into something that's useful or meaningful. Yeah, I think that's the big one. So, tree cover veg condition, does it contribute to that? I mean, these are all remote sensing products, but as I say, we could also link that. All of those could be correlated or linked to some sort of future prediction of productivity. Big one is, I mean, we're all assuming these systems are net sinks. They may not be a net sink. So, I mean, the Commonwealth's current abatement or climate change towards net zero at 2020, 2050 has got a huge sort of biogenic sink bolted in there, which we may or may not see. And that's what this would do. I think that's another utility to answer Alan's question. What's the point of all this going forward? And that might be something. I think Jenny wants to answer.
Yeah, thanks, Lindsay. That was great. And in fact, I think it's unfortunate that you finished with this last slide.
Yeah, I should have started with that.
As a person who works in both the top end and Central Australia, to have something that just squashes everything into the territory is just so frustrating.
Yeah.
I mean, it just doesn't, it's on most of those things you've got there, it's meaningless. So So the first thing would be to ask for, a savanna versus an arid zone distinction for a report card.
Nuance it
And-
a lot more.
I mean, I think everyone here in this room understands that, but it really worries me when you see this kind of thing being published.
Well, I think this year is a classic example where you've got the Alice region has had really above average rainfall, but then the guts of the NT's had disastrous rainfall. The Gulf's had none. And then we've got a big lump in Kakadu had a truckload of rainfall, and the Kimberley's had a shitload. Sorry about that, shouldn't swear.
It's just.
But the spatial variability is going to increase. So the interannual variability is going to go up, as is the spatial variability. And that's why this sort of remotely sensed link to towers on the ground, observing soil, temperature, blah, blah, blah. That's the other issue we're trying to grapple with is, can we get our tower network into the BOM? Gives them a whole bunch of sites in pretty remote areas. So they're a bit resistant because we're using different monitoring systems. They'd have to integrate it into their record, but they're getting there, they're coming. But only if we get good funding can we guarantee reliable data the BOM would absorb. So it just adds another metric to the whole milieu. Dr. J.
Would you like to comment on more on disturbance?
Yep.
And tell us a bit more about, do we have net sources or sinks in relation to cyclonic events and particularly fire, of course?
Well, if you recall to the joint paper we were all on in 2015, so the models will spit out the savanna as a sink, a weak sink. But then you take the bushfires people's emissions from the NAFI system, that sink disappears. And we actually have a landscape that's a net source. And that's the real dynamics. That's the NBP, net biome production. And that's the one that I think is what the atmosphere is seeing. So, and I think offset programs are missing these sort of offsets, forestry offset. All it's doing is measuring the change in biomass, but there's, if you have more biomass, you've got more respiration. So there's more to it than so I mean, some of these offset are really a partial carbon account. But what we did, I think, in 15 is what you might call a full carbon account, where you've got all the inputs from all the losses from termites, in particular fire. So fire is a game changer in certainly our environment. So that measuring that flux via fire consumes quite a lot of our time. And the tower doesn't do a great job. If you've got a fire front moving through your control space, I mean, you've got to throw your data out for that period where the fire is active, and only after perhaps 10 days. And some of Andrew's work was critical there, where we know, well, is the system now at some sort of equilibrium where we see the recovery of foliage, that post-fire reflushing, and that post-fire reflushing, that system is still a source for months after a hot fire. Big severe fire has a massive impact. It consumes 50% of the net ecosystem production, that big sink that we're measuring. So we really need to know about that fire big time. So that's why the integrating the NAFI data, the way we integrate the fluvial data to get a better picture on the losses is totally critical. So no, our North Australian systems are actually, if you believe our BS paper, a net source. So, but as we get more data, you can refine that, improve the modelling. We can get we can have another go. Anyone else? You've got a question. Can't you ask me tomorrow morning over tea? Oh no, it's Saturday.
You're probably close enough to Lindsay. Yeah, let's pull that.
So you talked about the net CO2 flux, or the net sink that you measured through your eddy covariance flux towers. I was wondering, how do these compare to much coarser top-down, the top-down global modeling? Do they compare well, and does it depend on sites?
Yeah, that's a great question, because as you've seen from the modelling, you're getting a range of potential outcomes. And I suspect the models are over predicting the sink, would be my gut feeling. And I've got we might be over predicting the sink as well, because we're not capturing that loss from fire particularly well. We're relying on the remote sensing almost entirely. But yeah, my gut feeling would be we're over predicting the sink. Yeah. Based on just looking at some of the outputs. I mean, often if I see a paper and I can get hold of the data for our pixels, I do it, but and some of them are okay, but yeah, some of them are well out. Yeah. And there's so many different groups using the data. The beauty of the TERN network is it's all open source. Everyone gets the data. The disadvantage of that, you get people who have no ability to sort of interpret and use wisely the data you've collected. So we are required by our funder to make it publicly available, which is great. ARC is the same, US is the same. But I see a lot of sort of slightly dubious interpretations of some of our information. There's no requirement of the person who downloads. We get 10 downloads a day. I mean, we tried to track it, we've lost track. So it's getting used a lot, particularly the flux data, probably because it's more, it's the organisation getting hold of the data is really quite good. But the way it's used is slightly problematic, yeah, slightly scary. I don't know if you saw the media about the offsets program. That was quite interesting. And this is sort of relevant to it. And no TERN data has ever been used in the offsets, modelling, full cam, any of that. There's a bit of a disconnect there. So that's quite interesting piece of information to have. All right, we had enough?
There's beers being